So this time we want to find the volume of the solid formed if we take region R, which is that region bounded by the functions y equal x squared and y equal the square root of x. And if we were to place tiles that are equilateral triangles in that region in such a way that those tiles are perpendicular to the x-axis, we get a solid formed that would look much like this. And to find the volume of that 3D solid, what we have to zero in on, and again, I'll let you look at the solid from some different perspectives, is if we can find the volume of one piece, then we can actually integrate to add up infinitely many volumes just like that. So there are infinitely many tiles that we can put in region R, and if we can find the volume of this one piece, and you can integrate to add up the volumes of those infinitely many pieces that look just like that. Okay, so in order to do that, we're going to go back and look at our region R, and I'd like to use the black pen. So again, region R was this region bounded by the functions y equal the square root of x and y equal x squared. This is region R. And again, let me erase. Didn't do that very well. What I need you to understand is we're looking at these equilateral triangles. We know all three sides are the same, and we know all the angles are 60 degrees. But what I need you to think about is this thing, as far as that tile is concerned, looks something like this. And again, what I need to be able to do here is I need to be able to describe the volume in terms of the area of the cross-section. So the volume of that one piece, we're going to find by taking the area of the cross-section, and we're going to multiply by the thickness. And that thickness is either some change in y or change in x. And again, that's the volume of just this one piece. If I go back to this diagram, I'm talking about this one piece right here. I want to find the volume of that one triangular shaped tile, and this is how we're going to do it. Okay, so in order to do that, I've got to know what this distance right here is. And again, if you go back and kind of correspond those two things in the figure, this segment that I'm talking about in region R, if I rotate here, if I rotate this, which is not going to let me rotate for some reason, okay, corresponds to the side of the triangle anyway. So here we go. Let's name the point. This is x comma square root of x. This point right here is x comma x squared. Again, remember when we name arbitrary points, we typically call them x comma y, but you can't name both of those points the same name because they do have the same x value, but their y values are different. This distance right here is going to be the top y value minus the bottom y value. And again, if I give some thickness to this, then that's going to be a change in x. Okay. As far as labeling that on our tile over here, that means that this side is square root of x minus x squared. This side is the square root of x minus x squared. This side is the square root of x minus x squared. But this height right here is a change in x. And again, just on the two-dimensional cross-section, we know all three sides are the same. And we know that the angles are all 60 degrees. Okay? Now, as far as finding the volume of this one piece then, we know the area of the cross-section. If you go back to pre-cal, you should have learned a formula that said the area of a triangle is always 1/2 a product of any two sides times the sine of the included angle. So I'm going to take these two sides, and that means this is the included angle. And that area is going to be 1/2 side sub 1 times side sub 2 times the sine of the angle that's included between those two sides. So it wouldn't have mattered what pair of sides we picked. These would have been the same. The angle would have still been 60 degrees. And again, the thickness that we have is going to be a change in x. Now for these problems, it's either going to be dy or dx based on which axis that your cross sections are perpendicular to. Now if I simplify that a little bit, this is 1/2 times the square root of x minus x squared squared. You should know that the sine of 60 is square root of 3/2. And so I guess completely simplified, then we would have a volume of that one piece of square root of 3/4 times the square root of x minus x squared squared dx. Now, we're not interested in just knowing the volume of that one piece. Go back and look at this. Not just interested in finding the volume of just that one piece right there. Okay? What I want to do is add up the volumes of infinitely many pieces that I can place in there, and then I'm going to find the volume of the solid that we have shown there. So in order to do that, to get our total volume here, we're going to integrate the square root of 3/4 times the square root of x minus x squared dx. And again, dx says our limits of integration have to be along our x-axis. Well, we found on the previous problem that these points of intersection were at 0, 0, and 1, 1. So our limits of integration on the x-axis are 0 to 1. And if you use your calculator to evaluate that, you should get approximately 0.056 cubic units.